Just I'm sharing my presentation. Okay, so in electromagnetism, we studied basic terms and definitions regarding to this magnetism. Okay, so we saw for the magnets, the direction of magnetic field that is towards and 2s. Okay, so you can see this magnetic field that is surrounded to these magnets. Now this direction of magnetic field that is given by the Fleming's right hand rule. Okay, so in according to the Fleming's right hand rule, when we just hold the conductor by the right hand, so the thumb points the direction of current flow, and then this bent finger that shows the direction of magnetic field. Okay, so according to that, we'll see how this current is coming in and coming out according to this Fleming's right hand rule. Okay, when current carrying conductor, so magnetic field is there. So how this current is flowing inside according to the right hand rule. So that we'll see. So for the current direction here, okay, is it visible this presentation?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So this cross mark indicates current is coming in. Okay, so you can see this direction is coming in A to B, and this dot mark indicates current is out, coming out. Okay, so this if you see this mark, either cross or dot marks, that indicates the direction of current according to the Fleming's right hand rule. So when the conductor is placed perpendicular to the plane of paper, then it shows that current is flowing into the plane. Okay, so the current is flowing into the plane, and shows that the current is coming, okay, flowing into the plane. And if we are just placed like this, then current is coming out, so that is shown by this dot line. Okay, so this cross that is coming in, and this dot that shows that current is coming out. Okay, so here written, the current flows into the plane of paper and direction of field is clockwise. So when cross mark is there, means when current is coming in, so current is flowing in clockwise direction. Then if dot mark is there, means if current is coming out, then uh, the current comes out of the plane of the paper, the direction of the field is anti-clockwise. Okay, so here field is clockwise and here field is anti-clockwise. So you can see the direction of current that is coming in, coming out, that is denoted by these cross marks and dot mark according to the Fleming's right hand rule when we hold the conductor. So this we discussed these basic terms. So here we saw some basic terms of magnetic circuit. You studied basic terms of electric circuit. So we are going to compare electric and magnetic circuit. So one by one, just I will tell you how we can differentiate this electric and magnetic circuit. Okay, wait for a moment. So just one by one, we will differentiate electric and magnetic circuit. So first here I have magnetic magnetic circuit. Here I have electric circuit. Okay, so first point is the closed path for magnetic flux is called magnetic circuit. Closed path for magnetic flux. So tell me for current, closed path for magnetic flux is called magnetic circuit. So here what I can say for electric circuit? Anyone? For magnetic circuit, closed path for magnetic flux. Here what I can say for electric circuit?
Closed path of electric current
Yes.
causes electric
Yes.
flux.
Yes, closed path for electric current is called electric circuit. Now second point is here we have flux. Flux is equal to, we can write mmf upon reluctance. Flux is equal to mmf upon reluctance. So here what I can write for electric circuit? Anyone?
Flux is equal to charge upon area.
No, in magnetic circuit we have flux. So what we have for electric circuit? Yes, current.
Current.
Good. Current equal to
Q by T.
EMF upon resistance. We have to show some similarity and dissimilarity. Here we are writing mmf upon reluctance. Here we have magnetomotive force. So here we have electromotive force. Here we have reluctance that provide opposition. Here resistance that provide opposition. Okay. So here we are going to some similarities. Okay. So this is similarities. Third, flux that is denoted by magnetic flux denoted by phi, unit is Weber. Here current denoted by I, unit is ampere. Okay. Now fourth one is, here we have mmf, that is in unit of mmf. mmf is equal to product of current and number of turns. So unit is ampere.
Amperes.
Okay, ampere turn, that is 80. So here we have EMF, unit of EMF in watts. Then reluctance S is equal to what you can write. S is equal to L mu 0 mu R A and unit of reluctance, that is ampere turn per Weber. So here we have resistance that is R equal to rho L by A, okay, in ohm. Now next similarities. Okay, wait. So sixth one we have permeance. Permeance is equal to permeance is equal to 1 upon
S.
reluctance. Yes, that is S. Here, what I can write?
Conductivity.
Permeance. So here I can write conductance.
Resistance.
Conductance. So it is equal to 1 upon resistance. Okay. Now seventh. Here we have permeability. So what we have here for electric circuit?
1 by mu.
Suppose permeability I am just denoted by mu. Here we have conductivity. Okay. That is denoted by sigma or delta. Here we have reluctivity. Here we have resistivity. Okay. Now we have flux density here. So flux density is given by B is equal to 5 by A Weber per meter square. For electric circuit, what I can write here? Current density. So current density, that is denoted by J. J is equal to I by A, and that is given by ampere per meter square. 10th point in similarity, magnetic field intensity. Magnetic intensity, that is H is equal to Ni by L ampere turn per meter. Here electric intensity, so electric intensity that is given by E is equal to V by D, that is volt per meter. So this is the similarities of electric and magnetic circuit. In these similarities, first dissimilarities is for magnetic circuit, the magnetic flux does not flow but is set up in the magnetic circuit. First one is magnetic flux does not flow but is set up, but it is set up in magnetic circuit. Kindly mute from your side. So here what I can write, the electric current actually flows in electric circuit. Here what I can write, electric current actually flows in circuit. Second dissimilarities, for magnetic flux there is no perfect insulator. For magnetic flux, there is no perfect insulator. Here, for electric circuit, there are number of insulators like glass, air, rubber, glass, air, rubber, mica. Okay. Third dissimilarity is at constant temperature, the reluctance of magnetic circuit is not constant but varies with respect to mu r. Here, reluctance is not constant. At constant temperature. Okay, varies with mu r. Here, at constant temperature, the resistance of electric circuit is constant and its value depend on resistivity, which is almost constant. So at constant temperature, resistance is constant. And fourth point in dissimilarities, once magnetic flux is set up in magnetic circuit, no energy is needed. So once magnetic flux is established, so there is no need of energy. Continuous of supply, okay, once field is established. Once magnetic flux is set up, no energy or no continuous supply is needed. Here, energy is needed as long as current flows through electric circuit. So we need here continuous supply. For to flow current in the circuit. Okay, so this is the similarities and dissimilarities of electric and magnetic circuit. So we'll be asked sometimes either ask similarities or dissimilarities. So according to the marks given, weightage given to the questions, so you need to write this point. Okay. So if you ask in 4 to 5 marks, then you need to write this all the means maximum points that you have to cover. Okay, for this similarities and dissimilarities. Now we will move to the Faraday's law of electromagnetic induction. So first law that indicates Faraday's laws of electromagnetic induction. So first law, whenever conductor cuts magnetic flux or field, EMF induced in it. Okay. And second, the magnitude of induced EMF that is directly proportional to the rate of change of flux. So that is given by the Faraday's law of electromagnetic induction. So in second law, we have in second law we have suppose n is equal to number of turns of coil. Okay, we have phi 2, that is final value of flux. Here I am considering phi 1, that is initial flux. Initial flux. This is final flux. And this is T, that is time for change of flux. Okay. Now initial flux linkages, that is initial flux linkages, that is N phi 1. Final flux linkages, that is N phi 2. This is N phi 1. This is N phi 2. So rate of change of flux, is equal to N phi 2 minus N phi 1 divided by T. Okay. So according to the Faraday's law of electromagnetic induction, the induced EMF is given by is equal to N phi 2 minus phi 1 divided by T. Okay, so this is nothing but N d phi by dt, that is rate of change of flux. So this is given by Faraday's law, the magnitude of induced EMF, that is directly proportional to the rate of change of flux. So according to the Faraday's N d phi by dt, but here according to the Lenz law, or we can say according to the right hand rule of Faraday's Fleming's right hand rule, the direction induced EMF direction that is coming in, coming out. Okay, so accordingly we can write this E is equal to minus N d phi by dt. So according to Lenz's law, suppose whenever there is current carrying conductor, so there is magnetic fields surrounding it. So due to current that creates its own magnetic field. So we have already, there is magnet, so that is having the magnetic field, and here current that producing its own magnetic field, so that is opposing it. So whenever a conductor or magnet is moving inside, so when N and N pole is created, so it oppose, and when N and S pole is created, so it attract to each other. So I will show through video how this Lenz law that is giving this, that has given this direction of current. So I will show the video of Faraday's law and Lenz law.
Electromagnetic induction.
Okay, is it visible?
No, sir.
No, sir.
No, sir.
No,
No,
sir.
sir.
Okay, okay.
No, sir.
No, sir.
Wait.
Electromagnetic induction can be demonstrated by learn about In this lesson, we shall learn about electromagnetic induction. The phenomenon of electromagnetic induction can be demonstrated by an experiment. Wind an insulated copper wire on a paper or wooden cylinder so as to form a coil in the form of a solenoid. Connect the two ends of the coil to a galvanometer and place a magnet close to it. The reading of the galvanometer is 0 when the magnet is stationary. The pointer of the galvanometer deflects towards the right when the north pole of the magnet is moved towards the solenoid. The galvanometer shows 0 reading when the motion of the magnet stops. This proves that as long as the magnet keeps moving, current flows in the solenoid. If the magnet is moved away from the solenoid, current flows in opposite direction in the solenoid. Thus, the galvanometer deflects towards the left. The deflection increases if the magnet is moved away with greater velocity. If the polarity of the magnet is reversed and the magnet is brought close to the solenoid, then current flows in an opposite direction. The galvanometer accordingly turns towards the left. Faraday observed that current flows in the coil only when there is a relative motion between the coil and the magnet. The direction of deflection in the galvanometer is reversed if the direction of motion is reversed. The current in the coil and the corresponding deflection of the galvanometer can be increased by using a strong magnet or by increasing the motion of the magnet. Increasing the area or the number of turns also creates a strong current in the coil. According to Faraday, when there is no relative motion between the magnet and the coil, the magnetic flux within the coil remains constant. So the galvanometer shows no deflection. But when the magnet is moved towards the coil or vice versa, the magnetic flux changes and an EMF is induced in the coil. If the circuit is complete, the EMF causes current to flow through it. Based on his experiment, Faraday formulated 2 laws of electromagnetic induction. Whenever there is a change in the magnetic flux linked with a coil, an electromotive force is induced. The magnitude of the induced EMF is directly proportional to the rate of change of the magnetic flux linked with the coil. The direction of the induced EMF depends on whether there is an increase or decrease in the magnetic flux. John Ambrose Fleming gave 2 rules to determine the direction of motion or the direction of induced current. While the left-hand rule is for electric motors, the right-hand rule is for generators.
Okay, so here for the machines for the direction of current, okay, for the motor we are referring Fleming's left-hand rule. For the generators we are referring Fleming's right-hand rule. Okay, so this is for the machines that we are applying this Fleming's right-hand rule and left-hand rule.
According to Fleming's right-hand rule, the thumb, forefinger, and middle finger of right hand are stretched perpendicular to each other. And if thumb represents the direction of movement of the conductor, forefinger represents the direction of the magnetic field, and the middle finger represents direction of the induced current. Lenz's law states that the direction of the induced EMF is such that it always tends to oppose the cause which produces it. Lenz's law obeys Newton's third law of motion, which states that to every action there is always an equal and opposite reaction. It also obeys the law of conservation of energy. It states that energy can neither be created nor destroyed. Therefore, the sum of all the energies in the system is a constant. Lenz's law is based on Faraday's law of induction. Lenz's law states that when an EMF is generated by a change in magnetic flux, according to Faraday's law, The polarity of the induced EMF is such that it produces a current whose magnetic field opposes the change which produces it.
So I will show the video, next video, how this magnetic field that opposes that is change in flux, okay, according to the Lenz law.
Lenz's law Lenz's law helps us to find the direction of the induced current in a loop when it is placed in a magnetic field which is changing. As the magnet moves towards the solenoid, this induces current in the solenoid. The induced current creates a magnetic field. The loop produces a north pole to oppose the magnetic field of the approaching north pole of the magnet. When the magnet stops moving, there is no changing magnetic field. The current in the loop is zero. Now, when the magnet is pulled away from the solenoid, there is a changing magnetic field in the loops of the solenoid. This induces current in the loop. However, this time the loop has a south pole generated, which attracts the magnet and opposes the motion of the magnet away from the solenoid. The induced current is therefore in the opposite direction.
Okay, so this is a demonstration of Lenz law. So whenever current is generated, that produces its own field. Okay, so when magnet is moving in, so we have N pole, that is magnetic field generated by current, so it opposes. And when magnet is away, then it creates a south pole, so it attracts. So it shows the direction of current accordingly. So according to the Faraday's law of electromagnetic induction, what we need, what arrangement we need? We need conductor or coil. Second, we need magnetic field or flux. And third, relative motion between magnetic field and conductor. Okay, so accordingly, we can generate the EMF and further it causes the current in the circuit. Okay, so Faraday's law of electromagnetic inductions, uh, that accordingly we can get the EMF and that causes the current, and second the magnitude of EMF, that is proportional to the rate of change of flux, and the direction of current, that is given by the Lenz law, or we can say according to the Fleming's right hand rule. Okay, so for the electric motor we are referring Fleming's left hand rule. For the electrical generator we are referring Fleming's right hand rule, okay, for the induced current direction. Okay, so now we have two terms, leakage flux and leakage coefficient. So leakage flux is nothing but the flux which is not useful. Okay, so in leakage flux,
सर
yes,
आगे वाले टॉपिक में एक डाउट है वो करंट जो होता है इंड्यूस करंट
okay,
वो वेलोसिटी के ऊपर कैसे डिपेंड करता है कंडक्टर की वेलोसिटी बढ़ाए तो इंड्यूस करंट बढ़ेगा
okay.
पूछ रहा हूँ मैं ऐसा वो होगा वीडियो में बता रहे थे इसीलिए
हाँ, तो according to the moving speed means as you know either conductor or magnets moving, okay, so whenever it going in or out, so according to that magnetic field is generated, so obviously it depends on velocity also. Okay, so when you have velocity is more, so accordingly you will have magnetic field is there, and accordingly current is generated. So obviously it matters. Relative motion that matters. Okay, or that velocity matters between field and magnet, between conductor and magnet. Are you
सर तो
getting?
वेलोसिटी तो नहीं बोल सकते ना, क्योंकि ईएमएफ वो फास्ट चेंज हो रहा है, तो वेलोसिटी के ऊपर डिपेंड हो ऐसा तो हम डायरेक्टली नहीं कह सकते ना, क्योंकि फेराडे ने भी ऐसा बोला नहीं है कि वेलोसिटी के ऊपर डिपेंड कर रहा है, वो ईएमएफ फटाफट चेंज हो रहा है इसीलिए हो रहा है.
Right, but we can say it also depends. It can depends on velocity. That we will see how this EMF is induced. V equal to Vm sin omega t. So in that we'll see V is equal to 2 pi f v2. So how it completes the whole round of magnetic field according to the velocity. So when you have velocity of magnets or conductors, so we'll have this current in the circuit accordingly. So it matters, this motion or velocity.
ओके सर.
Okay.
यस सर.
Now we have leakage flux. So leakage flux is nothing but the magnetic flux which does not follow the desired path. Magnetic flux that does not follow desired path is called a leakage flux. Suppose we have one conductor coil, so in that we have magnetic flux. Suppose here I have number of turns here, that is wound. Okay, current I is flowing. This is my core. Okay, so number of turns are wound. This is my flux inside. Okay, so this is a flux, that is useful flux that follows the path. Now some of the flux that is flowing in the magnetic core. Okay, so some of the flux that will be like this. Okay, this is my phi u, this is my phi L. Okay, this is my phi. So leakage flux means the flux which does not follow the desired path. Okay, so when current is passed through solenoid, so that is given here, magnetic flux is set up by it. Okay, so the most of the flux is set up in the magnetic core. This flux is known as useful flux. So this phi u, this is not the useful. This is called the useful flux. This phi, that is called the total flux. So total flux that is given by phi is equal to phi u plus phi L. So this unutilized flux, okay, or this leakage flux that is set up surround the core. Okay, that is not useful or that is not utilized. So this is your leakage flux, this is your utilized flux, and this is your total flux in the circuit. So the total flux of the circuit that is given by phi is equal to phi u plus phi L. Now, due to leakage flux, we have leakage coefficient. So leakage coefficient that is denoted by lambda. So it is the ratio of total flux to the useful flux. So total flux, that is phi. This is your phi u. So I can write this phi u minus phi L divided by phi u. Okay. And this lambda value that lies between 1.1 to 1.25. Okay, so this is the leakage factor, and this is the leakage flux. Okay, sometimes we have flux in the circuit that set up surround the core, and that is not follow the desired path of magnetic flux. So we have total flux is useful flux plus leakage flux, and this leakage coefficient that is given, and that range is 1.1 to 1.25. Okay, that is total flux to useful flux. So this is fundamentals of electromagnetics. Now we'll go in detail for the dynamically induced EMF, statically induced EMF. Okay, for the coefficient of coupling. So if anyone having doubt
So,
for yes,
so the total flux is useful flux minus leakage flux.
yes,
Shouldn't it be the addition sign?
yes. So it should be addition sign. Okay, this is addition, because we have this useful as well as this leakage flux. So is it addition of both? It is the addition of both. It is not subtraction.
So down in the formula you have written those, so that's why I got confused.
Okay, okay. Sorry. Here phi u plus phi l. Okay. What I can write, phi u plus phi l or phi u minus phi l? Anyone?
Plus.
5 plus 5L.
Sir, addition.
Yes, it should be
Addition
addition.
will come.
It should be addition. Okay, because we have both the flux, so we can do addition in terms of total flux. Okay, so it is 5 plus 5L by 5. So I have covered that fundamental terms of electromagnetics: Faraday's electromagnetic induction, Lenz's law, Fleming's right hand and left hand rule. Okay, and now we'll go for the dynamically induced EMF and statically induced EMF. Okay, in next lecture. But in next lecture, I am going to cover practicals. Okay, so this chapter will continue on next week lecture. Okay, so anyone having doubt regarding to this electromagnetics?
No, sir.
Okay,
No, sir.
to see these electromagnetic inductions, we need conductor or coil, we need magnetic field or magnetic flux, and third one is relative motion. If there is no relative motion, then we have nothing. Okay, so there should be relative motion between uh, conductor and magnetic field. Okay, if both are the stationary, then we haven't any effect. Means we haven't any magnetic field, or we haven't any EMF or current in the circuit. Okay, and according to the Lenz's law, it is giving the direction of current. So whenever we have solenoid arrangement, so due to the generation of current, so that produce its own magnetic field, so that oppose the original magnetic flux according to the direction of or moving of this magnet. Okay, when it is coming in, so it opposes. When it is going out, so it attracts. So according to that, we can show the deflection of current in the circuit. Okay, so yes.
सर आगे वो टर्न्स है, टर्न्स तो यूनिटलेस क्वांटिटी है, तो उसको क्यों यूनिट में हम इंक्लूड करते हैं? जैसे वो टर्न एम्पियर है, तो
Yes,
टी क्यों लिखता है? वो तो यूनिटलेस नहीं है।
it is dimensionless, but for showing this that coil turns that is given, but so it is dimensionless. It's okay, but just we are writing this ampere turn. Okay, it is, you are right. It is dimensionless or it is unitless, but we are writing this for denoting this turn. Okay, it is ampere turn.
ओके सर।
Okay, it is nothing but just we are indicating this n in terms of ampere turn. Okay, and I, so it is dimensionless, but for to show this n, this product, it is written ampere turn.
ओके सर।
Okay, so anyone having doubt regarding to this electric and magnetic circuit difference?
नो सर।
Okay, so I will share this. Okay, I prepared this question bank. I will share it soon. Okay, I'm showing you this question bank that we are going to cover.
पीपीटी रेडी हुई?
Some content that I need to edit, so I will share it in next week. Okay, or if possible, then I will share it in on this weekend.
ओके सर।
So you can see this question bank, this content you are going to study for this. Okay. So now I will move to this 4.10 induced EMF, dynamically induced EMF, statically induced EMF, self-inductance, expression for inductance, mutual inductance, and coefficient of coupling. Okay, so this is your unit number 4. And then we will move to this AC fundamentals. Okay. So I will share material of this unit 4 and question bank also that I will post in Microsoft Team. Okay, you may leave the session.
थैंक यू सर। थैंक यू सर।
Thank you, sir.